Good morning, good afternoon, and welcome to CGA's 2021 Wednesday webinar and virtual roundtable series. Today, amidst summer vacations, we are focusing on hydrogen, and we've got a great group on the line here. We do have sessions spanning the year until the end of November. My name is David McConkey, and I'm the Director, Operations, Safety and Security for the Canadian Gas Association. Today's session is entitled Strategies for Increasing Hydrogen Admissibility in the Natural Gas Pipelines. And our presenter is David Tycrobe, President, EE Energy Advisors, Inc. Thank you for taking the time and making the effort to participate in today's session. Before we start, let's take a quick look at our platform. On the left side of the screen, you'll find the virtual navigation bar. This is your main toolbar for the event, so please take some time to familiarize yourself with the features. Here you can start a chat or group chat with other attendees, see a full list of attendees registered, see sponsor details, and quickly access the full WWS program spanning to November. The chat will remain open during the entire span of the webinar series. Here you can also find the help guides and access technical support information. For the best experience, we recommend the use of headphones. Our platform is optimized for the Google Chrome browser. Please note, attendees can use phones or tablets to access the plenary sessions such as this, but only as a listen-only attendee. In order to access the full features, you have to be logged in on a computer. Once you're in a session, you will see the Live Now module on the left. Click Live Now to open up the features unique to the live session. Here you can see session details, rate and review the session, see speaker details, and ask a question. So as noted, today's session, we're focusing on hydrogen. We'll hear from David, and we'll have a brief, we'll have a robust Q&A session after his presentation. So with that, I'd like to introduce David Tycrobe, who will be presenting for us today. David is the president of EE Energy Advisors, Incorporated, and is also our key consultant at the Canadian Gas Association on our broader hydrogen file, including all the various initiatives that we have underway. You can see his bio on the event website, which you can access through the left side of your screen there. And with that, Dave, I'll pass it right over to you.
Thank you, David, and thank you everyone for taking some time out of your day for what I hope will be informative, even for those in the industry that are deeply invested at trying to understand a path forward with greater use of hydrogen. I hope to provide some new perspectives in the early slides of this deck, and then share with the entire audience as well the emerging pictures I think might be a larger hydrogen admissibility strategy for utilities, energy planners, for consumers in general as well. So let me there we go. Today's natural gas industry, the best way to state this is it's probably in a state of flux. What I provide is not a definitive outlook on the future, but I do think it's plausible that what we have today as gas infrastructure, increasingly going forward, and maybe relatively near term, is going to start having more variability in the gas supply. The composition today is relatively consistent, and going forward, we expect that both hydrogen in small but increasing amounts, renewable natural gas, and in many cases, the next generation of renewable natural gas or RNG will co-produce hydrogen, and we will have high hydrogen blending in some cases, with the potential for some markets to actually switch to 100% conversion of their natural gas networks. So we do expect that some markets will find for their climate change objectives or their economics, they will start to increasingly look at dedicated hydrogen networks for distributing that fuel as well. So when we look to this slide, I think one of the things that we are collectively challenged with is the cost of renewable fuels. When you take renewable natural gas or hydrogen today, and you look at that in the context of the affordability, it looks expensive compared to natural gas. And you can see this on this particular line down here, which is natural gas prices increasing with the escalation of a carbon price indice. But what you also see on the upper range is a group like the Hydrogen Council, a global body that what's emerging in hydrogen, and they are making projections at where you can create hydrogen that's green today and where it's going to be come 2030. But what's always missing from this is the perspective of how does this compare to other renewables? You do not compare renewable fuels to renewable electricity without looking at common units. And so this particular scale is normalized so that fuel pricing is dealt with in cents or dollars per kilowatt hour. I show markers here for the dollars per gigajoule, which would be common for those in the industry. Your home bill might actually be cubic meters rather than gigajoules. But the reality is, when you look at natural gas today, carbon price included, a little over 2 cents a kilowatt hour. Even at $40 a gigajoule, this is 14 cents or $140 a megawatt hour. That is economic in certain parts of Canada with mid-peak pricing. And then what we have is blue hydrogen. This is derived from, again, the Hydrogen Council's look at today and where it will be in the future. And we see the Canadian Biogas Association's outlook on renewable natural gas, and then a special call out for the assets and the opportunities in a market like Alberta and Saskatchewan, where carbon dioxide could be used in markets like enhanced oil recovery. These provide them with even a greater economic benefit to try and accelerate the path forward with taking carbon out of the fuel stream. But it really is important on the affordability discussion to be normalizing pricing on common units so we get better energy literacy amongst consumers, energy planners, regulatory officials. And I would argue personally that I find it disheartening that regulators and energy policy planners aren't trying to force this issue so that consumers become better informed at just what is or is not affordable today and what it looks like in the long-term outlook. But you can see that based on the Hydrogen Council and our current pricing regime for carbon as prescribed in Canada, you're going to see a convergence of renewable or low carbon fuels in the $43 to $70 a megawatt hour range. And the reality is that is most certainly affordable. And I'm going to talk about why it's even more so when we look at storage of energy. And the final piece that I'll talk about here is where we do have these early cost pressures for more expensive fuels. There are end-use technologies like thermal heat pumps or natural gas heat pumps that can deliver the same efficiency gains as electric heat pumps and take some of the bite out of any increased fuel cost for consumers. In essence, you can really help a consumer drive decarbonization along with still maintaining affordability by having both the decarbonized fuels arrive in the market, but also adopting those next generation of end-use technologies like thermal heat pumps. Now, I talked about the affordability as it related to just the commodity costs, but the reality is we can't get to any consideration of net zero in the long term without dealing with seasonal energy storage. You know, in a decade ago, when I toured with a number of US stakeholders, the executive teams of many utilities would say, if you love wind and solar, you've got to love storage. And in their context, they would talk batteries, they would talk compressed air energy storage, they'd talk pump hydro. But there is very little that they have at their disposal for long-term seasonal storage in the electricity industry. So when we start to look at what is available in the gas industry today, my belief is the gas network can own the podium for the most cost-effective renewable energy. It's not to say that everything should be gaseous renewable fuels versus electrification, but the flip side is very much true. We should not be looking at deep electrification without also deep decarbonization of the gas networks. And the reason really is because if we believe there is any likelihood of these economics coming to be with the right policy support over the next decade, then this is an imperative to try and keep consumers on side with the decarbonization plan, because you don't keep consumers on side without maintaining affordability. I would argue that if an end use can operate on renewable gas, that should be the priority. If you can't, and it's a end really is specialized for electric only, then by all means, that should be the priority, and we should increase the renewable supply in both the electric networks, the gaseous pipeline networks, and likely the liquid fuel networks as well. But it's because of this next piece on seasonal storage that's key. I think the picture on the lower right will be recognizable to many. That is Niagara Falls. It's basically in my backyard. But over the world, globally, that's an image that is recognizable for folks. What they may not understand is that that is also illustrating the vertical drop that the US and Canada use for a lot of hydroelectric generation. And in Canada, the Sir Adam Beck facility are 2,100 megawatts of low carbon electricity supply. That's 9% of this province's peak of 24,000 megawatts on the grid. But I'm here to tell you that that 24,000 megawatts pales in comparison to the natural gas network's peak day delivery of 80,000 plus megawatts. And so when you start to look at what it would take to replace that 80,000 megawatts in the gas grid that has seasonal underground storage, it's 40 Sir Adam Beck plants. It is a little bit outside of even the realm of normal thinking to think that you could tap that kind of resource. What's more daunting is the fact that it's the headwaters of Lake Erie that actually feed those hydroelectric stations. To do the same as the gas network, it would take 240 cubic kilometers of water feeding Niagara Falls in order to deliver that amount of energy. The gas industry each winter delivers that energy over 90 to 120 days. And more mind-boggling would be the fact that if you wanted to refill that storage after draining 50% of Lake Erie, it would take 1,000 days with the water flows through that Great Lakes system. If you can't see that there's benefits to diversity of how we decarbonize, knowing the ability of that gas storage today is $2 to $4 a megawatt hour, or less than a half a penny a kilowatt hour, then we really need to give a shake. And to kind of back this to another level of pan-Canadian look, you need to understand that Alberta's underground geological storage is many times larger than Ontario's. So these are assets, they're built, they're functional. We should be looking at how we leverage them in our long-term planning for decarbonization. Now, when we look at this, there's also, where do we get these renewable fuels? Where does hydrogen play a role? Often renewable natural gas has been looked at as landfill gas cleaned to pipeline standards, maybe a green bin program for a city where an anaerobic digester is going to convert that to biogas and we clean it up to pipeline standards. But those are the low-hanging fruit. They're what we do today. Whereas the next generation of renewable natural gas using more complex feedstocks, and these could be things like wood wastes, it could be sewage sludge, it could even be your municipal trash that in apartment towers like Toronto, Calgary, Montreal, source separation of organics, trash, and recyclables is very difficult. You can start to take these processes, and the state of Oregon would classify this as hydrogeneration or hydrogenation of these waste streams to create renewable natural gas. So these are the feedstocks that I've listed with hydrogen at the front end to basically create a renewable or low carbon methane supply. So that's where, in addition to any direct blending of hydrogen, hydrogen will play a much bigger role. And then we have the opportunity for natural gas with what's commonly referred to as blue hydrogen to convert to hydrogen from natural gas and have carbon capture and storage, or potentially the use of that CO2, so carbon capture and utilization, and we can get blue hydrogen. But in markets that don't have the geological resources of, say, Alberta or Saskatchewan, what we can do is what's called electrical reforming. So we can take a smaller amount of electricity than, say, electrolysis. We can, through the use of microwaves, break that natural gas with water into a reform process for hydrogen and get very dense, pure CO2 that can be used in a host of applications. Could be crop production for greenhouses, could be in cement making, could be in the production of next generation chemicals and fuels. These are the opportunities that are before us, so we continue to use conventional fuels and decarbonize. But more importantly, as on the left, renewable natural gas supplies increase, put through a process like this, we have the opportunity to go carbon negative. And that is just something that we don't talk a lot about when we talk blue hydrogen, is how it plays a role on decarbonizing conventional fuels, but plays a bigger role in the long term at going carbon negative for renewable fuels converted to hydrogen and have the CO2 sequestered. And then we have the electrolysis that many are familiar with, or what's commonly referred to as green hydrogen. And the good news is we're seeing much larger scale globally on the size of these facilities. The costs are starting to come down, but understand this is very much iterative. You just can't install these large plants and then say it's green hydrogen. If the input or that electron is not green, now we've got challenges. And so we're having to grow up in different stages or milestones, both sides of that equation. But the good news is the core technology in electrolysis is coming down in costs. And from the earlier slides, you'll see how the Hydrogen Council is looking at this globally and saying there is a path to affordability with green hydrogen. Now, to reinforce that strategic importance, by all means, we can directly blend in the natural gas network, small but increasing amounts. In some markets, we're seeing today up to 20% hydrogen by volume. But because the hydrogen is 1/3 as dense, it's about a 7% reduction in CO2 emissions. Now, some would say, well, that's not enough to get us where we need to be. But the important thing is to understand what that supply flexibility changes as we allow hydrogen to play a role, either through direct blending, or as I said, it's those next generation RNG supplies that produce both renewable methane, but co-produce that hydrogen. And so the flexibility of our pipeline assets to carry both those fuels in different compositions as a season might change or as time goes on, that will be important. And then we start to get to things like electrically derived fuels, or e-gas as it's sometimes known in some markets. And the moment we get to a pairing of the electricity networks and the pipeline networks with seasonal storage, you've got unmatched economics for delivering value to consumers on lower carbon energy, fuels and electrons, and the ability to meet their needs over that seasonal period, which is key in a market like Canada. But on that next generation renewable natural gas, we've got the more complex feedstocks that play a very important role, because today a lot of markets are competing for different feedstocks. You get price pressures because different markets are competing. The moment we bring these next generation technologies and expand the potential for different feedstocks, you have more potential to tap renewable fuels, but you have less competition, and that means the cost should start to come down, particularly as scale goes up. But I'm going to talk about how things like in situ underground methanation can play a role with hydrogen, and the emergence in markets like the US, Australia, on things like artificial photosynthesis. We're going to replicate what the tree does today. And that can be done with a variety of fuels in liquid or gas, but it is further out. But it was the solar industry 2 decades ago that was further out, and look where it is today as far as its commercialization and cost reductions. And so we start to look to the potential for those natural gas networks, yes, to be decarbonized, But increasingly, there will be targeted activities to say, why or how will we convert some of those existing natural gas networks to 100% dedicated hydrogen? And we're seeing that in markets like the United Kingdom with their UK's H21 project. This is serious efforts on their part. They are planning for large-scale conversions of some very aged networks, and they're proving out the safety case today as to how they will go about that between now and 2030. With the goal being the network of natural gas delivery today will be just as safe, if not safer, conveying 100% hydrogen by 2030. So there's work that they have to do. There's more research and deployments in new processes, but they're modernizing their grids to have that capability. And that is something I'll come to as far as grid modernization in a few slides. This really gives you that representation of how 20% hydrogen by volume, if we could start smaller today, as some utilities are at 2 to 5%, and grow that up to where some of the markets like Germany, the Australians in certain limited tests, and certainly in parts of Europe and the UK, they're demonstrating 20% hydrogen by volume today, a 7% carbon reduction. But then understand that it's those existing and next generation renewable gas supplies with that 20% hydrogen that start to pull us down this curve to a decarbonization without having to necessarily go to 80 or 70% hydrogen by volume in the networks. And then as you get to the renewable gas supplies decarbonized with things like the blue hydrogen technologies or electrical reforming, we get carbon negative. And so you can have a valid argument that conventional fuels will flow in the system, but the carbon negative offsets can certainly help Canada get to that true net zero out by 2050. And in some cases, we'll convert to 100% hydrogen networks. Now, from an innovation on gas storage, underground gas storage is not new, particularly in Canada. We've got a wealth of this at our disposal. What's very interesting is RAG Austria did a 4-year physical trial. This was not a paper study. They put a blend of up to 10% hydrogen with natural gas down in existing gas cavern storage and successfully demonstrated that despite that small molecule of hydrogen, there was no migration out of their reservoirs. They didn't compromise the reservoir integrity in any way. And just as importantly, they didn't have any microbiology that grabbed a piece of hydrogen and created sour gas or hydrogen sulfide by mixing hydrogen down the well bore with natural gas. And they held that for 6 and 12 months in 2 different trial periods to demonstrate this. Now, it's important to characterize this was for their specific gas reservoirs, their geology. So there's great insights that we could learn, but there's work that our utilities, our storage operators would need to do to say, could we do the same with ours? Or what process could we do that with, but change some of the operations? And so we're in a situation where we really do need to help the industry fund and support and work through those learnings. Yes, by grabbing the best practices from other parts of the world, but also from trying to say, how do we apply that to our specific characteristics? Now, the important thing to understand is that success over 4 years from RAG led them to what they call their Sun Conversion Project. Now, this is where they're going to take CO2 and they're going to put that down the underground storage reservoir. They're going to take renewable hydrogen and put that down in the reservoir and demonstrate that they get a natural underground methanation with those two, creating a renewable or lower carbon natural gas supply without a lot of fancy above ground equipment. So it'll be a natural process using below ground or in situ methods. Now, there's work they need to do. They may not prove that it's successful, but there's yet another example of innovation, and they are right now with early trials that are showing that they are likely to have success on this. So even if the CO2 was not renewable, and it could be in some cases, you're at least getting a recycling return of that CO2 with that renewable hydrogen. So I tend to refer to it as the hydrogen economy, looking at a energy blue box where CO2 gets recycled. How many turns can you recycle it? It's kind of like your aluminum cans at the curb. You certainly want to reuse it, recycle it before you go back to virgin aluminum for those cans. Now that brings us to what the Canadian Gas Association has been doing for some time on a global scan. What are the best practices that are happening elsewhere in the world? What can we learn? And more importantly, what might be a strategy for admitting hydrogen at a larger scale in Canada? We've tried to put this onto a single page, call it a strategy on a page. This is going to be circulated with the Canadian Gas Association members and others, but it tries to give a frame of reference for what could be key points to address in the short, medium, and long term. And part of this is, let's set an action plan over the next 4 years that you're not going to solve all this in the next 4. You won't solve all of it necessarily in the next 10, but it becomes a 4-year action plan that as you learn more, you revisit, you recalibrate, and underpinning that becomes the message that if nothing else today that you come away with, understand that grid modernization, what started as smart grid on the electric systems for greater integration of renewables, is just as applicable to grid modernization of the pipeline assets. How do we modernize these pipelines to have the flexibility for greater renewable content, including hydrogen blending? And this has been a completely absent discussion. But without that grid modernization, you're asking utilities to say, how do we take a safe operating asset today, and we're not just going to put something in it that we don't understand the full magnitude of what might change? Could be safety, could be operational, could be billing. So there's, just like the electric grid, when they put smart meters out for the electric grid, they had to have grid modernization support to change their processes, including data and IT back office. The same is going to apply to decarbonizing the pipeline grids. But these grids exist, they're bought and paid for, they're cost effective today, they're unmatched for seasonal storage. We would be with real questionable thought processes if we aren't starting to apply some form of support for grid modernization so they are a long-term viable asset. Now I'm going to talk about some of these buckets that are in here for what's a 10-point plan with very specific actions in here, albeit at a high level. But there is codes and standards work from the Canadian Standards Association, both on their pipeline codes, but also their end user equipment codes, what's commonly referred to as the B149 installation code for natural gas equipment. Now, they tend to be rather silent on hydrogen, but the good news is there's work underway with the CSA. The Canadian Gas Association utilities are looking at this, and there's global best practices what we can leverage. Likewise, and I'd say this is one of the more important things, signaling to the market that we are going to expect increasing hydrogen concentrations. And we can paint a picture as to 2030, 2040, 2050, and it helps get the balance of the industry, whether it's pipeline makers, metering vendors, end use equipment vendors, to understand, gee, when I'm starting to plan the next generation of gas technology, it should have the capability to operate on some variability of fuels with hydrogen included. The gas metering, the CGA is undertaking efforts with Measurement Canada to help them understand what should be done in the measuring space. And there are some longer term items around our high pressure transmission networks and feedstock customers that may use gas in the process or manufacture of chemicals. These all need to be understood. That doesn't mean you need all this solved to start, but you need to start working through. And part of that is also in expanding the regulatory framework. You already have a gas industry with a safety track record that is a very strong credential. there is no reason why the processes and operations of the gas utilities can't be leveraged so that, yes, they will have conventional natural gas networks. They will have those networks with blended fuels with certain amounts of hydrogen and RNG, and they may start to have dedicated hydrogen networks, if not for repurposing to feed end-use consumers like homeowners, then to move sources of renewable hydrogen to their blending stations. And so there is a need for that regulatory framework to start contemplating how we could leverage everything that the utilities do today and just extend to them that mandate to go forth, update, modernize their processes, make sure things are in place, including with first responders, as we change the composition of gas to be able to facilitate that longer term transition. So I'll call this the 3 pillars. They were on that screen, but these are the ones that I think are fundamental for us to start thinking in a far more serious way about. That grid modernization is key. We did this for the electric grid. We're still doing it, and primarily for reasons of having more renewable integration. There are other things that are part of that, resiliency, etc. But that grid modernization is just as applicable to the pipeline networks. And we don't have that mandate today. We're not embracing that gas grid with that sort of modernization strategy. And some of that is in the areas of material composition. How do we ensure that as we replace and update materials, that they've got that long-term compatibility with hydrogen so that not just 2 or 5% could be blended, but 20%. Maybe full conversion is possible without doing an awful lot in the future. And then we need to signal to appliance vendors and others, even the energy regulators, expect more variability in that gas composition. And there's no reason, I mean, today the electric grid is very specific. If you go outside the technical parameters for voltage, frequency, you get failures like what we had in big parts of the US and, Eastern Canada, predominantly Ontario. I think it was 2003, where tree trimming caused the grids to black out. That was because there is very tight tolerances on what can be done. We don't want to replicate the same tight tolerances on the gas composition that can go in the pipelines, because today they can take fairly significant changes in pressure. There's no reason they can't take wider variations in fuel composition. And the end use appliances that are using that fuel need to also have the same flexibility. But we're seeing that, and I'll talk about that in some of the final slides. When we look to that regulatory framework, as I mentioned earlier, that safety culture, the operational processes, they're there to be leveraged for hydrogen and blends of hydrogen and growth in renewable natural gas the same way they've been leveraged for decades. And we need to figure out how to leverage that and bring that for consumers. The work done in something like the United Kingdom's H21 project, in addition to grid modernization and all the technical issues they worked through, a big part of that was consumer and social engagement. They wanted to understand what the public thought of higher hydrogen blends, and also what the public thought about having their household appliances running on hydrogen. The good news is, by and large, consumers were quite receptive to that because they had belief in the same utility that was delivering safe, reliable fuel today would be doing that job tomorrow and long term, just with a different composition. But the consumer didn't have to worry about what that composition of fuel was. And so we start to look to the blending as part of this, the conversion as part of this to hydrogen, and that regulatory model needs to evolve to look at that so we don't have a mishmash that confuses consumers and others. But then how on the next stage of hydrogen and transportation, could be for heavy duty trucks running on hydrogen, could be on trains, could even be the mass market fuel cell electric vehicles. How could you have the hydrogen hub strategy established in key nodes throughout the gas networks today? They could feed hydrogen into the gas grids. And as those consuming loads for dedicated hydrogen, say heavy duty trucks, grow up over the next 5-10 years, the hydrogen's already being produced. It's already being delivered into the natural gas networks. Now we just change where the priority market is if a market like transport starts to show up, and you get a strategy that embraces with market pull today, where the pipelines can take that hydrogen if we do this correctly on policies, procedures, and grid modernization. And it's there as a resource where the gas utilities could be part of that transportation network just by having the same hydrogen that was produced for pipelines available as a dispenser for a vehicle. And so we're seeing that with level 3 charging stations on the electric grid. This is what needs to be contemplated on that path forward or that roadmap for greater integration of that hydrogen hubs using the existing natural gas networks. Now, under those near-term priorities, I talked about the codes and standards. I said CSA has a significant effort underway on both their pipeline codes, that's the Z662, and also their end-use codes, the B149.1. They've set a task force that's actually working through this with a mandate that when they refresh the next set of standards and codes, they will start to look at how hydrogen needs to be identified in that. But there are other companion codes and standards such as cooktop ranges. Now, in the United Kingdom, Europe, they're looking at dedicated hydrogen cooktop ranges. Sounds a bit strange for everyone who's always worried about hydrogen. Gee, that's a dangerous fuel. And they're looking at ranges that'll be in people's houses the same way gas ranges are today, on 100% hydrogen. So they're dealing with the aspects of the safety standards that need to evolve with this. And that's where I think modernization, you could have government and regulatory support to help fund that at a more accelerated pace. And then there's the materials, and there's a great wealth of opportunities to mine and leverage work already done in different parts of the world. But make no mistake, the gas utilities here need to look at that data, the best practices, and say, all right, I still need to do some significant inventory of my assets, look to what I need to prioritize, how I prioritize the modernization of it. And so there really is that opportunity to reach out to federal and provincial stakeholders and say, can we expand your grid modernization support so it looks at both the wires and the pipeline assets? It will pay dividends to consumers and help us get to that decarbonization quicker. Now, as an example, I've mentioned the United Kingdom's H21 project. What's interesting is this was funded by Ofgem, one of the key regulatory stakeholders in the United Kingdom. This is 5 utilities, one's a transmission company, 4 distributors, but the initial round of support, and it's grown since then, was close to 18 million Canadian, all to enable those utilities to grow their processes, procedures, to identify what needs to be modernized in their networks. And as I said earlier, the objective here is not just hydrogen blending, but 100% conversion of those gas networks to hydrogen by 2030, and in certain pockets earlier, as early as 2023 for trials. And the objective is that the safety will remain where it is today or improve with 100% hydrogen. Now, they're working through that, but there's a wealth of information that speaks to what those utilities have been able to do with their regulator and the government to start this meaningful progression towards decarbonization, with hydrogen playing a very big role and the pipeline assets continuing to be a very significant part of the energy infrastructure in the UK. But to look at another market, Australia, has their renewable hydrogen programs, and that's through their funding body ARENA. But what's interesting is they saw some grid modernization out of that with what needs to happen for ATCO Australia and Australian Gas Networks to fast track the development of rather large scale hydrogen blending and natural gas networks. So there they didn't call it out just as grid modernization, but certainly they're looking at what's needed in order to drive that through to something that could enable wider use of hydrogen in the natural gas networks. And then for gas metering and system monitoring, as I said, the Canadian Gas Association is already engaged with Measurement Canada, looking at global scans, many of the existing gas meters today all suggest higher hydrogen blends are permissible. The European regulator has identified maybe there's a bit of a concern with one particular class of turbine meters. They've said it's good for up to 10% hydrogen today. They're researching that further, and what we're seeing is it's not likely the meters physically that are going to be the big question mark. It's going to be, how do we start to look at hydrogen's effect on energy content and any kind of variability, predominantly affecting in the early days large industrial and commercial users because they use so much fuel. But we need to have these energy contents accurate even for the residential bills. Now, what I propose is that there's an opportunity for the next generation of smart metering on gas, particularly for the large industrials, where we could start to have real-time monitoring of the hydrogen composition, where we could true up or adjust the energy content so that those industrial consumers, large commercial consumers, are getting billed accurately. And then we could start to expand that to how we understand blends in different parts of gas networks. So even the mass market residential blends or meters are trued up accurately for energy content. But it goes beyond that. There's no reason why real-time sensing of hydrogen at the meter, particularly for industrials, could not be used to then send a signal to those industrials saying your composition of hydrogen is X. And in Europe already, we're seeing the cogeneration vendors on large-scale cogen plants taking a real-time signal, adjusting their parameters for the turbines or engines so that they maintain emission compliance. There's also no reason why in the future you couldn't have a situation where if there was a gas leak detected in the premise, it wouldn't send a signal back to that meter and create a lock condition so that you resume a safe status in the household. These are the things around modernization of these assets, including something as simple as what today is a gas meter, to start and focus on energy content billing, because I would argue you don't want to be like the electric industry, very tight on parameters. You want the flexibility for variability on hydrogen content, RNG content. Take advantage of the fact these are flexible assets, and let's not paint ourselves into a picture where we take away that flexibility and by extension the economics. Just a little bit on the innovation on what could feed the metering and what I discussed as possibly a large industrial energy calibration system. Companies like the Gas Technology Institute in the US, MEMS AG in Europe, they're looking at microprocessor sensors for hydrogen to be able to, in very tight tolerances, have a computer type device send a signal as to what the real-time composition of hydrogen in a gas stream is. And the accuracies are at a level that would suggest they could be in existing Measurement Canada accuracy requirements. So these are things that, like the computer chips and their declining costs, this doesn't have to be an expensive proposition for the industry. We just need to leverage what's there from the work being done by the GTIs and the MEMS AG to say, how do these different microprocessor sensors for hydrogen get integrated into our systems? Now, we already see hydrogen-ready appliances coming in markets like the UK. Two appliance vendors in particular have hydrogen-ready appliances. Worcester Bosch and BDR Thermea. These could run at 0 to 20% hydrogen by volume with natural gas, no changes to the appliance. And then if in the future, it's maybe is 10 years old, but the gas utility is converting it to hydrogen, call a service tech, have the hydrogen burner replaced from a factory burner into these existing boilers that are set up for natural gas. It's more cost effective. The UK's identified it as a key platform going forward. But what was very interesting was the need to think differently. Here we're talking today about blending X%, maybe up to 20% of hydrogen by volume with natural gas, and what are the issues. But these appliance vendors are already looking at what happens if we take 100% hydrogen networks, and on a peak day requirement, maybe we need to give it a bit more of natural gas to carry us through the peak day? Could a 100% hydrogen boiler operate on 20% natural gas blending? Now, you wouldn't do this if you've got fuel cells connected or other direct hydrogen users that are sensitive to this, but this is the type of thinking that's going on in those markets like the United Kingdom and the Netherlands to say, how do we handle those peak day requirements and still achieve our decarbonization? So keeping flexible in our thought process and open to different ideas is going to be key. And so finally, in summary, I just need to underscore that it's not just hydrogen blending directly, it's that next generation renewable natural gas that's going to co-produce hydrogen and RNG. They're clearly part and parcel, bundled together as part of that long-term decarbonization plan for natural gas networks. When we start to look at grid modernization, is absent and it's needing to be rectified. We need to get to the point where pipelines and wires are both looked at as having to be modernized and improved upon to get greater integration of renewable gas supplies. And then finally, under that administration or admissibility strategy for hydrogen, again, this is not locked in stone. It will be in consultation with the industry, but I do think some key pillars, maybe this is more than a three-legged stool, but we do need to signal to the market that we expect this to be happening. We can always adjust as we learn more, but we need to the end uses, that the materials, they all need more flexibility than what they have today. And it's not necessarily that they don't, it's that we don't understand, is it good to go now or does it need a little bit of a change? The regulatory framework and leveling that playing field will be key. From a near-term, the CSA and others are already with efforts underway to upgrade the codes and standards. You can see some of the ideas around enhanced metering, but again, these things need to start now, and they could be accelerated with some key support from either regulators or government policy when it starts to come to how we have the gas utilities step up to this. And they're already doing this in a meaningful way, but how could we make that path easier for them, for consumers, for appliance makers, etc. And so with that, thank you. Hopefully that was some different perspectives than maybe what you would have had.
Thank you very much, David. Very dense coverage on the topic there. Just a reminder for everyone, now is our Q&A period. You can ask a question. If you go to the left, you see that Live Now red bullet. Through there, if you scroll down, you can ask a question. So we invite everyone to send questions along. We've got a couple, but I just wanted to go through a bit of a kind of set of key takeaways that I jotted down as you were going through, Dave, your presentation, but my list just got longer and longer. So I'll probably just go through a couple of them, but you said one of the key takeaways you noted was this concept of grid modernization that exists on the electric side, and it should also exist on the natural gas side. You noted the three pillars of an admissibility plan, the first of which was grid modernization, signaling to the market that hydrogen is going to be increasing in the flows of gas in our systems, which kind of gets at that supply and demand chicken and egg question. Regulatory and code framework is required to be in place to allow these things to happen. You also noted some of the near-term priorities, codes and standards, and materials. Your comparison with the Adam Beck hydro facility was excellent, indicating that we need 40 of those facilities in order to meet the daily delivery of natural gas in Ontario. A striking comparison there. You also in one of your charts where you see the blending of hydrogen going down to going up to 100%. You noted that in order to achieve that full carbon reduction, you don't actually need 100% hydrogen, because there's many other processes that you can leverage that become available as you introduce hydrogen into the system. So that was interesting. see my list is long. You noted the need to have a direct comparison of pricing on our bills, and I think that's an important one. That folks really need to think about. Being able to look at your natural gas bill, look at your electricity bill, and be able to compare them really easily, allowing the consumer to understand and therefore make choices according to better understanding. You noted if you love renewables, you have to love storage. Again, another important point. You noted you're not going to keep end users on board without affordability. There are a few other things, but perhaps that's a sufficient list of takeaways. I'll kind of delve into some of the questions that have showed up, but again, everyone feel free to throw some more in there. So kind of related to your H21 UK program that you were talking about, there's a question from Dimitri at TC Energy. Can you, let's go to this one here. Can you, with the new gas stream composition, what kind of change would be required for end use devices? So burners, heaters, etc.
Yeah, so what's interesting is they are finding a path forward that allows them on blending today to not blanket statement 100% say they can get to 20% with existing legacy appliances, but they are finding there's probably more flexibility at higher blends than they expected. And if you look at an appliance life cycle where over 10, 12, 15, 20 years at the outset that they are going to have to replace and modernize those equipment. This is why Bosch, BBR Thermea, as appliance vendors, they're advocating that by 2025, they think every new gas appliance should be certified hydrogen ready. And then not only has it a prescribed certified 0 to 20% capability that utilities can plan around, consumers can plan around, but then they've got a path to a OEM burner that can drop in as well. For the transmission companies, we didn't get into a lot of detail here, but on a material side for gas distributors, plastic networks are looking to have a great deal of flexibility for potentially full hydrogen distribution. On the steels that run at higher pressure, there's work even underway in Germany where this is more of a paper study right now, but the early findings are suggesting that they could take a high pressure gas transmission network, repurpose to 100% hydrogen. The capital cost would probably be about 15% of a new dedicated pipeline. And so these are lessons learned, or call it markers in global activity, that we can say, let's make sure we understand it, but how could utilities, regulators, governments invest to bring those lessons learned and then have our utilities apply them to their own networks?
Related to that, there was a question, what's the maximum amount of hydrogen you can put in an existing pipeline without causing the embrittlement?
There's a number of technical factors. So on the gas distribution side in the H21 project, they're looking at dedicated hydrogen as high pressure steel that they will probably purpose build, or they'll look specifically at how to upgrade those transmission assets. But then on the plastics, they don't have those embrittlement issues. They're finding that the seams, the joints, the procedures for repair, they're all robust under high hydrogen or dedicated hydrogen use. When it comes to the steel assets, this is another area of grid modernization that I think governments and regulators need to say, look, what's being learned in other markets like Germany, let's make sure we don't reinvent the wheel. But then each gas operator is going to have to say, how do I apply those lessons learned to my network, my inventory of assets? And then over 5, 10, 15 years, what could be my modernization of replacing maybe sections of a plant that are questionable for dedicated hydrogen? What might I need to do in more regular maintenance regimes, such as sending a integrity device down the pipeline to make sure I don't have cracks or other things that could cause problems. So it may not be a change of any materials, it might be a change of the maintenance regime. But that's where that grid modernization support enables our utilities to move quicker and understand what they need to do.
Thank you. Question about the impact to LNG. So increasing levels of hydrogen, what's the impact expected to the LNG industry?
Yeah, that's an interesting one. Certainly the hydrogen and natural gas have different points where they liquefy, hydrogen being much cooler. Now, for an LNG plant, they take gas as a feedstock, they liquefy it for whatever need, including export. My own belief is there's probably an opportunity for a two-stage process where liquefying a blend of fuel is going to cause the hydrogen to still come out as a gas. The methane gets refrigerated, and now you've got a source of relatively pure hydrogen that could be used. But the expertise has not been applied to that. So they are one example of a feedstock customer where we need to say, what needs to be done? Do we take the hydrogen out upstream of the liquefaction or LNG process? Do we let it go through and find a way of getting cost-effective hydrogen out? Or what are other issues? And we're seeing that out of Southern California Gas, where for transport of blended fuels and then at a refueling station for trucks or cars, they are looking at electrocompression that isolates the hydrogen molecule, pulls that out separately. So there are separation processes that can be used if needed. We just need to understand the feedstock customers and what's possible today and what maybe is a good investment in some future research.
So we're getting down to the wire, but we've got a few additional questions here. Maybe we can just go through quickly a few questions about appliances again. Are there examples of natural gas forced air furnace manufacturers that can take hydrogen or a combination at this stage now?
Yeah, if you look at the work, and some of this has been done by some of our Canadian utilities, and I don't want to make blanket statements. I mean, one of our utilities actually found that one of the appliances they were somewhat, I won't say concerned, but they had caution around was gas fireplaces. You want that visibility or luminous flame. As you put hydrogen in, it tends to reduce some of that luminous or the attractive value. Now, at low percentages like 2 or 5, that's probably not too significant, but they're worried about a consumer saying, gee, I think I could make a tweak on this appliance. Could I, could I get back what I want? There's ways of dealing with that, but on the mainstream appliances, more and more testing is showing that we've got a progression path forward. Certainly up to 10% looks doable, but you can't just make the blanket statement today. There's more work to be done to say, okay, if this is the case on a European boiler, what's different around the natural gas furnace in North America, if anything? And again, there's just some rigor or some process to say, can we now move to a wider network of end-use appliances that are deemed suitable for X%? But every year that goes by, we learn more as a global gas industry about increasing those concentrations. It's just got to be done in that path or mindset towards doing it safely.
I'll package these two together. So question about challenges at blending hydrogen at higher operating pressures. And then the other question is just obviously H2, I mean, hydrogen is a small molecule. So what are challenges relative to it escaping, through joints and valves and things like that? You can answer those two.
Yeah, so I think, on the leaks, let's separate high pressure from the general system, including what's in our houses. So Kiwa, a testing agency out of the Netherlands, what they call their high house. If you Google high house report, Kiwa, you're going to end up with a rather in-depth study around putting dedicated natural gas, hydrogen blends up to a certain percentage, like 20%, and full hydrogen flowing through existing pipes in houses, and what were the leak characteristics. And what you find is that some of the characteristics might change, but in general, they found that because hydrogen is so much more buoyant, it wants to get out of any areas where it might be trapped if it ever did leak in a house, that the safety conditions by and large are still deemed to be safe. At the higher pressures, what we end up with is some material issues that probably are a bigger issue than leaks through joints. We start with understanding what happens with not just embrittlement that you mentioned, crack propagation growth, some of these other things, and what are the mitigating factors. In some cases, if you had a short section of high pressure transmission line, there are now high pressure plastic composites that can be pulled through like a sleeve to bring full integrity without some of those negative material properties that would happen at, say, high or dedicated hydrogen. But high hydrogen in steels at high pressure today is done throughout the world, including big parts of the North American Gulf Coast, where hydrogen pipelines are, operating at high pressures and doing so safely. So we need to understand how we take those lessons to the legacy natural gas assets and then say over 10, 20 years, how do we modernize that so that they continue to function for decades to come?
Excellent. We'll leave it there. There's a few other questions, but we're just over time. So, David, thank you so much for your remarks and expertise. Before we close out, I want to remind everyone of the entire Wednesday webinar series that we have running. If you found this session valuable, we encourage you to share the overall program with your colleagues. Again, you can find that on your left in the platform. Invite them to join future sessions. Recall that sessions are recorded, and you can contact us in order to understand how to access those if you're not sure. Also, we'll be back online Wednesday, August the 25th with our Measurement Canada, our annual update, as you see on the screen there. So with that, I'll close today's session by thanking once again Dave Tykerobe, our sponsors, which you see on the screen there. Thank you very much. And Can Events for orchestrating our session today in the background. And thanks all of you for joining us for this WWS. With that, we'll bid you a good summer, and we'll see you next time.
Thank you, David. Thank you, everyone.